To examine this epileptic spike, NetStation will show the conventional EEG over on the left as a strip chart. The blue and red and white map at the top shows the pattern of EEG across the head at that point. At the bottom, the dark lines show the butterfly plot, which is the overlay of all of the EEG features of all channels at once. As we look at this first small blip in the butterfly plot, we can look at it in the map and the butterfly plot. We can also look at it across the head with all 256 channels, where the texture and pattern of the EEG can be rapidly seen. As we go to the onset of the large spike, we see that the beginning is a different pattern that has a positivity in the left posterior region. This appears to be the onset of the big spike, and then as we progress up the spike peak, we see the peak is quite different, that the left anterior region, the dark blue up on the left top of the head, shows that region. So the question is, what's going on with the apparent propagation or movement of the spike over the head? To do that, we'll look at the 3D plot, where we see the very beginning onset as a dark blue on the back of the head. And then the question is, can we relate the EEG channels to the MRI of this person's brain? The first thing we have to do is align the sensor positions, digitized with geodesic photogrammetry, precisely with the MR image. The next thing we have to do is to look at the registration of the MR and the segmentation of each of the brain tissues, here shown in color, overlaid with the patient's MRI. Each brain tissue has a different conductivity. We must characterize that conductivity as we relate the measured EEG on the head surface to the generating sources inside the brain. Once we validate the tissue segmentation and the exact electrode positions, we can then go in to look at the localization, the inverse of the surface EEG as it's generated inside the head. This allows us to look at the dynamics of the epileptiform activity in specific brain regions. So we'll go back to the plot and we'll look at the same spike progression, but now instead of only looking at the surface, we'll look at its activity inside the head. So the first small blip we see is starting here in the left anterior temporal lobe, the yellow area on the right side of the image. We're looking at the bottom of the brain here. And then as we go on to the big spike, we see again that the positivity in the left posterior, that's created by this negativity in the left temporal region around the hippocampus. Now watch the interplay between that hippocampal activity in blue and the anterior temporal, the periamygdalar activity. There is this ping pong activity, excitability shifting between the left posterior and the left anterior before the spike peak finally has a clear left anterior focus. So we have two key brain regions that we have to understand the propagation of this epileptiform activity. One is in the left posterior region. We look at the dipoles that are generated from each cortical patch. The other is the left anterior region. These regions become candidates for testing seizure onset, such as in long-term monitoring, potentially leading to targets for surgical resection. And also these can be targets for non-invasive neuromodulation, such as with the geodesic transcranial electrical neuromodulation technology.